On July 1st, 2025, a telescope in Chile detected something that shouldn't exist. An object moving at 68 kilometers per second, traveling on the most extreme trajectory ever recorded with an orbital eccentricity that breaks the laws of physics as we know them. This visitor carries the designation 3I Atlas, and it represents the third confirmed interstellar object to invade our solar system. But unlike the mysterious Oumuamua or the familiar Borisov, this cosmic intruder is different. It's bigger, faster, and more active than anything we've encountered before. This comet could be up to 24 kilometers across, making it potentially the largest interstellar visitor ever detected. It's racing through space with a hyperbolic trajectory that will carry it past Mars, around the Sun, and back into the void forever. We have only months to unlock its secrets before it vanishes into the darkness between stars. Prepare yourself for the most shocking interstellar discovery of our time. We begin. Late in the evening on July 1st, 2025, Larry Deneau, a software engineer at the Atlas telescope in Chile, was processing routine observations when something caught his attention. A faint dot of light, magnitude 18, moving across the star fields near Jupiter's orbit at an impossible speed. It looked like a completely routine discovery, Deneau recalls, but the preliminary calculations made his blood run cold. The object wasn't just moving fast, it was moving at speeds that should be impossible for anything bound to our solar system. At 68 kilometers per second relative to the Sun, this object was traveling far faster than any solar system object should be able to move. The Atlas Survey telescope had stumbled upon something extraordinary. The object, initially tagged with the cryptic designation A11PI3Z, was entering the inner solar system from the direction of Sagittarius, arriving from the very heart of our galaxy. But this wasn't some ordinary comet making a return visit after thousands of years in the outer darkness. The mathematics were undeniable. Such speeds ensure objects will slip through the Sun's gravitational grasp. Anything moving this quickly simply can't hang around long. Rather than following a typical elliptical orbit, this object's blistering speed was carving out a hyperbolic trajectory, a path that takes it swooping through the inner solar system before soaring back to the interstellar void. Within hours, observatories across the globe were turning their most powerful instruments toward this mysterious visitor. The Minor Planet Center received over 122 observations from 31 different observatories within the first 24 hours. Professional astronomers and amateur observers alike realized they were witnessing something unprecedented. The object was officially designated 3I Atlas on July 2nd, marking it as only the third confirmed interstellar object ever detected, passing through our solar system. The Roman numeral 3 placed it in an exclusive club that includes the mysterious Oumuamua and the familiar comet Borisov. But 3I Atlas was already proving to be unlike anything astronomers had seen before. Early observations revealed something even more remarkable. This wasn't just a dead rock tumbling through space. Telescopes detected clear signs of cometary activity, including a faint coma and a tail stretching at least 25,000 kilometers through space. After millions of years drifting through the frigid depths between stars, this ancient visitor was awakening as our sun's energy began heating its icy surface. The discovery timeline was about to get even more shocking when amateur astronomers made a disturbing revelation about what NASA had missed. What NASA didn't want you to know is that 3I Atlas had been visible in their telescope images for weeks before the official discovery. Amateur astronomer Sam Dean, working from his home computer, systematically searched through archived Atlas data and made a shocking discovery. Dean found clear images of the interstellar visitor dating back to June 25th through 29th, extending the observation timeline by crucial weeks. But that wasn't all. Yequanzi located even earlier observations from the Zwicky Transient Facility, spanning June 14th through 21st. The evidence was undeniable. This cosmic invader had been photographed multiple times before anyone in the professional astronomy community recognized what they were looking at. Sam Dean suspected that 3I Atlas was not discovered earlier because it was passing in front of the galactic center's dense star fields, where the comet would be hard to discern among billions of background stars. The object had been hiding in plain sight, camouflaged against the most crowded region of the night sky. The extended observation timeline allowed for devastating precision in calculating the object's true trajectory. With weeks of data instead of days, astronomers determined that 3I Atlas has an orbital eccentricity of 6.2, the most extreme trajectory ever recorded for any object passing through our solar system. To understand how extreme this number is, consider that Earth's orbit has an eccentricity near zero, representing a nearly perfect circle. Even Halley's Comet, with its highly elongated 76-year orbit, reaches an eccentricity of less than 1. When eccentricity exceeds 1, objects follow hyperbolic paths that enter our solar system once and never return. But an eccentricity of 6.2 represents something almost beyond comprehension. The amateur astronomers had exposed a fundamental failure in our detection systems. How many other interstellar visitors had passed unnoticed simply because they traveled through inconvenient regions of the sky? Professor John Tonry from the University of Hawaii admitted that quite a few interstellar objects come through our inner solar system each year, though 3I Atlas is by far the biggest to date. The pre-discovery observations also revealed why automated systems failed to flag the object earlier. The comet was traveling through the galactic plane where star density reaches maximum concentrations, creating a visual chaos that confused detection algorithms designed to spot moving objects against relatively empty backgrounds. This revelation raised disturbing questions about our planetary defense capabilities. If we could miss a massive interstellar comet for weeks, what else might be approaching undetected? The answer would soon become clear as astronomers realized the true scope of this cosmic invasion. 3I Atlas is moving at 68 kilometers per second relative to our Sun, shattering every speed record for interstellar visitors and redefining what we thought possible for objects traveling between star systems. To comprehend this velocity, imagine traveling from New York to Los Angeles in less than 90 seconds, or circling the entire Earth in under 10 minutes. This speed is so extreme that it places 3I Atlas in a category beyond anything previously observed. The mysterious Oumuamua reached speeds of 26 kilometers per second, while comet Borisov traveled at 32 kilometers per second. 3I Atlas is moving more than twice as fast as any confirmed interstellar object in recorded history. Such speeds ensure that objects will slip through the Sun's gravitational grasp without slowing down. The escape velocity from our solar system varies with distance from the Sun, but typically ranges from 42 to 45 kilometers per second. 3I Atlas exceeds this threshold by such a massive margin that our Sun's gravity barely affects its trajectory. The physics behind such extraordinary velocity tells a story of cosmic violence that occurred millions of years ago in a distant star system. Objects don't achieve these speeds through gentle gravitational nudges. 3I Atlas most likely came from the outskirts of some other planetary system, where it was ejected from its orbit around an alien sun by catastrophic gravitational interactions with a giant planet or a passing star. The comet's trajectory analysis reveals it has been approaching from the general direction of Sagittarius, where the central region of our galaxy is located. This path suggests it may have originated from the galactic disk, the flat plane where most stars in the Milky Way reside. Computer models suggest that achieving such extreme velocities requires multiple gravitational encounters or single catastrophic events. Binary star systems, supernova explosions, or close encounters with stellar mass black holes could provide the tremendous energy needed to accelerate objects to these speeds. The comet has likely been traveling through interstellar space for millions or even billions of years, before recently arriving at our solar system. What makes this speed even more remarkable is that 3I Atlas shows no signs of slowing down. Unlike objects born in our solar system that follow predictable elliptical orbits, this visitor will maintain its velocity as it races past the Sun and continues its eternal journey into the darkness beyond. The comet's hyperbolic excess velocity, when far from the Sun, measures approximately 60 kilometers per second, confirming that it will exit our solar system at nearly the same speed it entered. After its brief encounter with our cosmic neighborhood, 3I Atlas will disappear into the void between stars, carrying whatever secrets it holds back into the galactic darkness. But this record-breaking speed creates an urgent problem for astronomers racing to study this cosmic messenger before it vanishes forever. The orbital eccentricity of 6.2 that defines 3.1 Atlas represents mathematics so extreme that it challenges our understanding of what's possible in gravitational dynamics. This number encodes the story of the most violent cosmic event ever recorded in our solar system's vicinity. Understanding orbital eccentricity requires grasping the fundamental shapes that objects can follow through space. A perfect circle has an eccentricity of 0, representing the most stable possible orbit. Earth's slightly oval path around the Sun measures just 0.017, keeping our planet at nearly constant distance from our star throughout the year. Most objects in our solar system follow similarly well-behaved orbits. Even highly elongated paths like that of Halley's Comet reach eccentricities of only 0.967. These are bound orbits, mathematical curves that close upon themselves and repeat indefinitely. When eccentricity exceeds 1, the fundamental mathematics change completely. Objects begin following hyperbolic trajectories, open curves that stretch toward infinity without ever returning. This is exactly what defines interstellar objects. Their hyperbolic orbital paths prove they originated outside our solar system and will never return. But an eccentricity of 6.2 represents something almost beyond theoretical limits. 3I Atlas follows one of the most open hyperbolic trajectories possible, barely influenced by our Sun's gravitational field even during its closest approach. The object is moving so fast that solar gravity can only slightly bend its path, like trying to redirect a bullet with a gentle breeze. Harvard astronomer Avi Loeb has calculated that such extreme orbital parameters create untenable mass densities in interstellar space, unless 3I Atlas represents an incredibly rare population of cosmic wanderers. The mathematics suggest that either this object is much smaller than initial estimates indicate, or interstellar visitors like it are far rarer than previously calculated. The precise trajectory calculations reveal additional shocking details. 3I Atlas entered our solar system on a path inclined 175 degrees relative to the ecliptic plane, meaning it's traveling in a retrograde direction almost opposite to planetary motion. This extreme inclination provides additional confirmation of its alien origin and suggests it experienced complex gravitational interactions during its journey through interstellar space. The comet will reach perihelion on October 29th at a distance of 1.356 astronomical units from the Sun, placing it just inside the orbit of Mars. During this closest approach, 3I Atlas will experience maximum solar heating, potentially revealing its true composition and internal structure through spectroscopic analysis. The mathematical precision of these calculations allows astronomers to predict exactly where this cosmic visitor will travel during its brief passage through our solar system. 3I Atlas nearly became the ultimate interstellar visitor that escaped detection entirely, camouflaged against the most challenging observational background in the entire night sky. For crucial weeks, this massive cosmic wanderer traveled through our solar system completely invisible to automated detection systems, not because it was too faint, but because it was hiding in the worst possible location for astronomical observations. The object's orbital path carried it directly in front of the galactic center, the incredibly dense heart of our Milky Way galaxy, where billions of stars create a brilliant, overwhelmingly crowded backdrop. Imagine trying to spot a single snowflake during a blizzard of light, and you begin to understand the monumental challenge astronomers face. This region toward Sagittarius contains the highest concentration of visible stars anywhere on Earth's night sky, precisely where the central region of our galaxy is located. The massive galactic bulge creates such an extraordinarily dense stellar field that distinguishing individual moving objects from static background stars becomes almost impossibly difficult. Automated detection systems, specifically designed and optimized to spot moving objects against relatively empty star fields, struggle tremendously in these visually chaotic regions. Sam Dean, the amateur astronomer who eventually found the crucial pre-discovery observations, noted that 3I Atlas likely remained undetected for such an extended period precisely because of this cosmic camouflage effect. The irony of this near miss is staggering. 3I Atlas arrived from the general direction of Sagittarius, potentially carrying invaluable scientific information about star formation processes and planetary system evolution from the most dynamic region of our galaxy. Yet, its very origin among the dense star fields made detection nearly impossible using current automated survey techniques. The galactic center region presents unique observational challenges that extend far beyond simple star density. Interstellar dust clouds scatter and absorb light, creating complex patterns of brightness and darkness that confuse automated detection algorithms. Gravitational lensing effects from massive objects can distort the apparent positions of background stars, making it even more difficult to identify genuinely moving objects. Only when 3I Atlas finally moved away from the densest concentration of background stars did automated survey systems begin flagging it as potentially unusual. By that time, precious weeks of potential observation time had already been lost forever, though fortunately enough remained for comprehensive scientific study. This near disaster highlights a crucial and previously unrecognized weakness in our current detection capabilities. How many other interstellar visitors have passed unnoticed, simply because they traveled through inconvenient regions of the sky? The University of Hawaii's John Tonry admits that quite a few interstellar objects come through our inner solar system each year, suggesting our detection rate represents only a tiny fraction of actual visitors. The revelation forces us to confront an uncomfortable truth about cosmic surveillance and planetary defense. Initial observations suggest 3I Atlas could be up to 24 kilometers in diameter, making it potentially the largest interstellar object ever detected and dwarfing both previous cosmic visitors by enormous margins. If these size estimates prove accurate, this discovery represents an entirely different class of interstellar wanderer. The mysterious Oumuamua measured only a few hundred meters across at most, while comet Borisov's nucleus was estimated at just 400 to 500 meters in diameter. 3I Atlas appears to be an order of magnitude larger, potentially 10 times the diameter of previous interstellar visitors. However, determining accurate size measurements remains extraordinarily challenging because 3I Atlas is an active comet surrounded by a bright, reflective coma of gas and dust. Astronomers normally use distant objects' brightness as a proxy for size, but comets' ejected material interferes with such estimates, meaning the actual dimensions could range anywhere from 5 to 50 kilometers in diameter. The comet appears especially bright because it passed opposition on June 25, 2025, causing its surrounding dust cloud to be brightened by an opposition surge effect. This optical illusion occurs when sunlight reflects directly back from dust particles, creating enhanced brightness that can dramatically skew size calculations. Harvard astronomer Avi Loeb has calculated that the combination of size and number density estimates leads to untenable mass densities in interstellar space. His analysis suggests that either the core radius of 3I Atlas is smaller than 400 meters, similar to Borisov's dimensions, or objects of this size represent an incredibly rare population with much lower number density than initially estimated. Nevertheless, 3I Atlas appears to be weakly active compared to the other interstellar comet Borisov, suggesting it may indeed have a substantially larger nucleus that produces less gas and dust per unit surface area. This behavior pattern could indicate different composition or internal structure compared to typical solar system comets. The size uncertainty stems partly from the comet's extremely faint apparent magnitude of 17 to 18, requiring sophisticated telescopes and exceptional observing conditions for detection. Most amateur telescopes cannot detect objects fainter than magnitude 15, placing this interstellar visitor well beyond the reach of casual observation. Advanced observatories, including the James Webb Space Telescope's infrared capabilities, should soon help clarify 3I Atlas's true dimensions and composition. Infrared observations can detect thermal emissions from the solid nucleus itself, distinguishing between heat from the core versus reflected sunlight from the surrounding dust cloud. The larger size has profound implications for understanding the violent processes that eject objects from their home planetary systems into interstellar space. Time is rapidly running out for humanity's investigation of 3I Atlas, creating unprecedented urgency among the global astronomical community as this once-in-a-generation opportunity threatens to slip away forever. The comet will remain observable through September 2025, after which it passes too close to the Sun for safe telescope observations. Solar glare will then hide the object until early December, when it re-emerges on the opposite side of our star, already beginning its exit from the solar system. Planetary astronomer Coretta observed the comet using the Lowell Observatory's Discovery Telescope in Arizona as soon as he heard about it. He believes it will only be a couple of weeks before just about every large telescope on Earth and in space has made time to spot and track the comet. People are excited. Almost every planetary astronomer I know immediately ran to a telescope or sent emails requesting telescope observing time in the next few days, Coretta reported. While we might have several months to study this fascinating object, the earlier we can figure out how it works, the quicker we can plan for the rest of its passage through the solar system. European Space Agency astronomers are tracking the object using telescopes around the world as part of their broader mission to detect and characterize potentially hazardous objects. By the time 3I Atlas was officially announced, the Minor Planet Center had already collected 122 observations from 31 different observatories. The challenge intensifies because 3I Atlas currently appears at magnitude 17 to 18, requiring sophisticated equipment and dark skies for detection. According to current estimates, the comet may brighten to magnitude 16 by the end of July, though these predictions remain uncertain given our limited experience with interstellar visitors. The situation becomes more complicated as the comet approaches perihelion. From October 2nd through November 10th, 3I Atlas will be less than 30 degrees from the Sun, making observations extremely difficult or impossible for ground-based telescopes. The comet is currently around 4.5 times as far from the Sun as Earth, but it will reach its closest point to the Sun on October 30th, coming within 1.4 astronomical units of our home star. Shortly before this happens, the comet will also make its closest approach to Mars, coming within 0.4 astronomical units of the red planet. During the comet's close approach to Mars, it may reach an apparent magnitude of 11 from the planet's perspective, which means Mars orbiters may be able to observe it with unprecedented detail. This represents a unique opportunity for spacecraft already positioned in the Martian system to study an interstellar visitor at close range. After disappearing behind the Sun, 3I Atlas will reappear in early December, offering astronomers another window for study, though the comet will be significantly fainter and less active during its outbound journey. The December reappearance represents humanity's final chance to study this cosmic messenger before it vanishes into interstellar space forever. The distinctly reddish glow surrounding 3I Atlas tells an ancient story written in cosmic dust, revealing precious secrets about its mysterious origin and chemical composition from an alien star system. Observations from the Fox Telescope North clearly show that the comet's developing coma displays a reddish hue, definitively indicating the presence of complex organic compounds and dust particles. This characteristic coloration closely resembles that observed around Borisov, the previous interstellar comet, strongly suggesting fundamentally similar formation processes in the cold outer regions of different planetary systems. The Nordic Optical Telescope observations conducted by renowned astronomers David Jewett and Jane Liu confirmed that 3I Atlas was clearly active with a diffuse tail. Miguel Alarcón and his team at the Instituto de Astrofísica de Canarias discovered cometary activity with a tail stretching at least 25,000 kilometers through space. The reddish coloration provides crucial scientific information about the chemical processes that occurred during the comet's formation billions of years ago. Complex organic molecules form through various pathways during planetary system evolution, and their presence reveals information about the potential for prebiotic chemistry in alien environments. Spectroscopic analysis of the escaping gases and dust will reveal the detailed chemical composition of 3I Atlas's ancient nucleus, providing direct samples of material from another planetary system. Each molecule has a unique spectral fingerprint, allowing astronomers to identify water vapor, carbon monoxide, carbon dioxide, methane, ammonia, and increasingly complex organic species within the expanding coma. The dust particles being released contain invaluable information about high-temperature processes that occurred during the early formation of the comet's birth system. These microscopic grains preserve records of condensation sequences, thermal processing, and dynamical mixing that shape the distribution of materials throughout the original planetary disk. The size distribution of dust particles provides additional insights into the comet's activity patterns. Larger particles indicate recent activity from the nucleus surface, while smaller grains may have been processed by cosmic radiation during the extended interstellar journey. The observed ratio between different particle sizes helps determine how active the comet was in its original system versus how much material is being released now. Closer looks with more powerful observatories, including the James Webb Space Telescope's infrared capabilities, should soon help clarify 3I Atlas's composition with unprecedented detail. Infrared observations can detect thermal emissions from microscopic dust grains, revealing their precise temperature, size distribution, and chemical composition. The chemical signatures preserved in 3I Atlas represent some of the most pristine material available for studying conditions in another star system, offering insights into planetary formation processes throughout the galaxy. For millions or even billions of years, 3I Atlas has endured the most extreme survival conditions in the known universe, drifting through the frigid void between stars, where temperatures approach absolute zero and deadly radiation constantly bombards any exposed surface. During its extended voyage through interstellar space, the comet experienced temperatures of -270°C, cold enough to freeze any known material into brittle crystalline structures. At these extreme temperatures, most chemical reactions completely cease, and even the motion of individual atoms within molecules slows to nearly imperceptible levels. The radiation environment of deep space presents equally challenging survival conditions. High-energy cosmic rays, accelerated to tremendous speeds by distant supernovae and other violent cosmic events, constantly bombarded the comet's surface throughout its multi-million-year journey. These energetic particles can break apart complex molecular structures and gradually alter the chemical composition of exposed materials. Galactic cosmic radiation includes everything from individual protons and electrons to heavy atomic nuclei traveling at significant fractions of light speed. When these particles strike a comet's surface, they create cascades of secondary radiation that can penetrate several meters into solid ice and rock, potentially altering subsurface materials that will only be exposed when the comet becomes active again. Despite these harsh conditions, 3I Atlas appears to have retained its structural integrity and chemical composition remarkably well, as evidenced by its ability to develop a normal coma and tail when heated by our sun. The fact that it can outgas normally suggests that internal ice deposits remain largely uncontaminated by radiation damage or thermal cycling effects. The comet's survival provides valuable information about the resilience of materials under extreme conditions. Understanding how complex molecules and ice structures withstand millions of years of radiation exposure has important implications for astrobiology and the potential preservation of organic compounds in space environments. Theoretical models suggest that objects like 3I Atlas can maintain viable chemical compositions for tens of millions of years during interstellar travel, potentially carrying complex organic molecules between star systems. This possibility raises fascinating questions about whether life's building blocks might occasionally spread through the galaxy via interstellar objects. The surface layers that experienced direct radiation exposure during the journey may have developed protective crusts that actually helped preserve underlying materials from further damage. This creates natural time capsules of pristine ancient material that formed in an entirely different stellar environment. The successful preservation of volatile compounds through such an extended cosmic odyssey demonstrates the remarkable stability of materials under extreme space conditions. The extreme velocity of 3I Atlas tells a story of catastrophic violence that occurred millions of years ago, when this cosmic wanderer was violently ejected from its home system by forces that transformed an ordinary comet into a galactic bullet racing through space. Objects don't achieve such tremendous speeds through gentle gravitational nudges. 3I Atlas most likely came from the outskirts of some other planetary system, where it was ejected from its orbit around an alien sun by catastrophic gravitational interactions with a giant planet or a passing star. The physics behind such extraordinary acceleration involves scenarios that would completely destroy smaller objects. Multiple sequential encounters with giant planets can create devastating slingshot effects, with each gravitational interaction adding tremendous energy to an object's motion. Computer simulations show that objects can occasionally achieve hyperbolic escape velocities through precisely timed planetary encounters during periods of orbital instability. Stellar close encounters represent another mechanism for producing such extreme velocities. When two star systems pass within a few light-years of each other, their gravitational fields interact to fling objects from the outer reaches of planetary systems into interstellar space at tremendous speeds. The gravitational chaos created during such encounters can accelerate objects far beyond normal escape velocities. Binary star systems offer additional possibilities for violent ejection. When two stars orbit closely together, objects in the outer regions experience complex three-body gravitational effects that occasionally result in hyperbolic ejection trajectories. The gravitational dance between multiple massive objects creates chaotic dynamics that can unpredictably accelerate smaller bodies to extreme speeds. The most dramatic ejection mechanisms involve stellar evolution itself. When massive stars reach the end of their lives and undergo supernova explosions, the tremendous energy release can accelerate nearby objects to significant fractions of light speed. While 3I Atlas's velocity falls far below such extreme levels, asymmetric supernova explosions or interactions with neutron stars could potentially provide the necessary acceleration. Recent theoretical work suggests that planetary system instabilities during late heavy bombardment periods, similar to what our own solar system experienced billions of years ago, routinely eject significant numbers of objects into interstellar space. These chaotic phases occur when giant planets migrate through developing systems, gravitationally scattering countless smaller bodies. The violence required to achieve 3I Atlas's current velocity suggests it experienced one of the most extreme gravitational encounters possible while still remaining intact as a coherent object. Understanding these ejection mechanisms helps astronomers estimate how many interstellar objects should be traveling through our galaxy at any given time. The discovery of 3I Atlas provides shocking confirmation that our galaxy is filled with cosmic wanderers, with University of Hawaii's John Tonry revealing that quite a few come through our inner solar system each year, although 3I Atlas is by far the biggest to date. This admission from a leading astronomer exposes the uncomfortable truth that our detection capabilities have been missing the vast majority of interstellar visitors. For every object bright enough and well-positioned enough for detection by current survey systems, dozens or hundreds of similar cosmic wanderers likely pass through completely unobserved. Statistical analysis based on the 3 confirmed interstellar detections suggests we're seeing only the tip of a massive iceberg. The detection bias heavily favors objects that happen to pass relatively close to Earth and arrive from convenient viewing angles. Interstellar visitors that traverse the outer regions of our solar system approach from problematic directions, or arrive during periods when Earth-based telescopes cannot observe them, remain completely invisible. Current estimates suggest that at any given time, thousands of interstellar objects larger than a few meters across may be present within our solar system. The vast majority remain undetectable due to their small size, great distance, or unfavorable geometric circumstances for observation from Earth. Theoretical models predict that the size distribution of interstellar objects follows similar patterns to asteroids and comets in our own solar system, with vastly more small objects than large ones. While 3I Atlas represents an unusually large specimen that aided its detection, the cosmic population probably consists primarily of much smaller bodies that current technology cannot reliably identify. Mario Juric, an astronomer at the University of Washington and discovery software lead at the Vera-C Rubin Observatory, explains that the new facility should uncover many more visitors from beyond our solar system, allowing astronomers to study them as a population rather than scattered, isolated discoveries. The Rubin Observatory alone is expected to discover between 1 and 10 interstellar objects annually once it reaches full operational capacity, representing a dramatic increase over historical rates. This technological revolution means the era of interstellar visitors as rare, unexpected discoveries is rapidly ending. The hidden population likely includes representatives from many different types of planetary systems throughout our galactic neighborhood. Each object carries unique information about its birth system, offering opportunities to study chemical compositions and formation processes of worlds we cannot directly observe. Chris Lintott from the University of Oxford describes interstellar objects as our chance to randomly sample what's going on in the rest of the galaxy, providing insights into planetary system evolution across diverse stellar environments. The accumulation of data from multiple interstellar objects will eventually allow comprehensive statistical comparisons between different stellar environments and their associated planetary building blocks, revolutionizing our understanding of how common Earth-like worlds might be throughout the cosmos. October 29, 2025 marks the moment when 3I Atlas will swing closest to our Sun, reaching perihelion at a distance of just 1.356 astronomical units and potentially unleashing the most spectacular cometary display ever witnessed from an interstellar visitor. As the comet approaches within 130 million miles of our star, placing it just inside the orbit of Mars, solar heating will reach maximum intensity, triggering massive outgassing events that could transform this cosmic wanderer into a brilliant spectacle visible to powerful telescopes worldwide. The approach timeline reveals a series of dramatic encounters that will test the comet's structural integrity. On October 3rd, 3I Atlas will pass within 0.19 astronomical units of Mars, approximately 29 million kilometers from the red planet. This represents the closest approach any confirmed interstellar object has ever made to another planet in our solar system. Mars orbiters, including the Mars Reconnaissance Orbiter, Mars Express, and the HOPE probe will have unprecedented opportunities to study an interstellar visitor at close range. From Mars's perspective, the comet may reach apparent magnitude 11, making it easily detectable by spacecraft cameras and scientific instruments already positioned in the Martian system. These observations could provide the most detailed measurements ever obtained of an interstellar object's surface properties, composition, and activity patterns. The spacecraft will be able to track changes in the comet's coma and tail development as solar heating intensifies during the final approach to perihelion. The increasing solar energy will cause subsurface ices to sublimate at accelerating rates, potentially exposing fresh material that has remained unchanged since the comet's formation in another star system billions of years ago. Spectroscopic observations during this phase will reveal the most pristine samples of alien chemistry ever analyzed. However, the timing presents a cruel irony for Earth-based observers. When 3I Atlas reaches perihelion on October 29th, Earth will be positioned on the opposite side of the Sun, making direct observation impossible during the moment of maximum activity. Ground-based telescopes will lose sight of the comet as it disappears behind solar glare. The comet will remain unobservable from Earth until early December, when it reemerges on the far side of the Sun, already beginning its journey back to interstellar space. By that time, 3I Atlas will be retreating from the inner solar system, growing fainter and less active as it moves away from the solar energy that drove its spectacular awakening. This observational window represents humanity's final opportunity to study this cosmic messenger before it vanishes into the void between stars, carrying its secrets back into the galactic darkness, where it will drift for millions of years before potentially encountering another star system. The James Webb Space Telescope represents humanity's most powerful weapon for unlocking the secrets of 3I Atlas, offering unprecedented capabilities that could reveal the true composition and structure of this interstellar visitor with shocking clarity. Webb's advanced infrared instruments can detect heat radiation and molecular signatures that remain completely invisible to optical telescopes, opening entirely new dimensions for understanding materials from another star system. The telescope's position at the L2 Lagrange point provides optimal geometry for extended observations as the comet approaches and passes perihelion. The near-infrared spectrograph can simultaneously observe hundreds of different wavelengths, creating detailed spectral maps that reveal the presence and abundance of numerous chemical species within 3I Atlas's expanding coma. Water vapor, carbon monoxide, carbon dioxide, methane, ammonia, and complex organic compounds all emit characteristic infrared radiation that Webb can detect with remarkable precision. Webb's mid-infrared instrument offers complementary capabilities for studying the thermal properties of dust particles being released from the comet's nucleus. By measuring infrared heat radiation emitted by microscopic grains, astronomers can determine their temperature, size distribution, and chemical composition with unprecedented accuracy. The thermal measurements provide crucial insights into the comet's internal structure and activity patterns. Different regions of the nucleus may heat up at different rates as the comet approaches the Sun, creating temperature variations that reveal information about surface composition, subsurface thermal properties, and rotation characteristics. One of Webb's most valuable capabilities involves detecting extremely faint infrared emission lines from trace species that might be present in tiny quantities within the comet's atmosphere. These measurements could potentially identify complex organic molecules or unusual isotopic ratios that provide clues about exotic chemical processes in the birth system. The telescope's exceptional stability and sensitivity allow for time series observations that track how 3I Atlas's activity changes as it approaches the Sun. These temporal measurements can reveal how different chemical species respond to increasing solar heating, providing insights into the physical structure and composition of the ancient nucleus. Webb's infrared capabilities also enable observations that penetrate through the dusty coma to study thermal emission from the solid core itself. This direct view of the nucleus can provide accurate size estimates and surface temperature measurements that are impossible to obtain using optical wavelengths, where dust scattering dominates observed brightness. Coordinated observations using Webb's multiple instruments will create comprehensive portraits of 3I Atlas that combine chemical analysis, thermal mapping, and temporal monitoring into unified scientific datasets. These integrated measurements will provide the most detailed characterization ever achieved for an interstellar object. The results could revolutionize our understanding of planetary formation processes around other stars and potentially reveal whether the building blocks of life are common throughout the galaxy. 3I Atlas appears especially bright because it passed opposition on June 25, 2025, causing its surrounding dust cloud to be brightened by an opposition surge effect that has confused initial size estimates and created a cosmic optical illusion. Opposition surge occurs when sunlight reflects directly back from dust particles surrounding the comet's nucleus, creating enhanced brightness that can increase apparent magnitude by factors of 2 to 5. This phenomenon explains why 3I Atlas seemed much larger than expected when astronomers first attempted to calculate its dimensions based on brightness measurements. The timing of this opposition surge coincided almost perfectly with the comet's discovery, meaning that initial observations captured 3I Atlas at peak brightness rather than its normal appearance. Astronomers normally use distant objects' brightness as a proxy for size, but the surge effect dramatically skewed these calculations. Harvard astronomer Avi Loeb has analyzed the brightness data and concluded that the combination of apparent size and estimated population density leads to untenable mass densities in interstellar space. His calculations suggest that either 3I Atlas is much smaller than initial estimates indicate, or objects of this size represent an incredibly rare population. The opposition surge effect gradually diminishes as the comet moves away from perfect alignment between Earth, the object, and the Sun. This means that ongoing brightness measurements will reveal the comet's true baseline magnitude, allowing for more accurate size determinations as observational data accumulates. Current brightness estimates suggest 3I Atlas may be magnitude 17 to 18 under normal conditions, significantly fainter than the enhanced brightness observed during opposition. This correction brings size estimates down from the initial 24-kilometer maximum to more conservative ranges of 5 to 15 kilometers in diameter. The confusion highlights the challenges of studying interstellar objects with limited observational experience. Unlike solar system comets that have been observed through multiple orbital cycles, interstellar visitors provide only brief observational windows with no opportunity for long-term brightness monitoring. The brightness surge also affected spectroscopic observations by increasing the signal-to-noise ratio for chemical analysis. The enhanced brightness during opposition made it easier for telescopes to detect faint spectral lines from trace gases and complex molecules in the comet's coma. As 3I Atlas continues its approach toward perihelion, astronomers will track how its brightness changes in response to increasing solar heating. These measurements will separate genuine activity-driven brightness variations from the artificial enhancement caused by opposition geometry. The lessons learned from this brightness surge will improve analysis techniques for future interstellar visitors, ensuring that size estimates and activity measurements account for geometric effects that can dramatically alter observed properties. Unlike the baffling Oumuamua that sparked wild speculation about alien technology, 3I Atlas behaves exactly as astronomers expect a normal interstellar comet should behave, following predictable physics without mysterious accelerations or unexplained properties that defied scientific explanation. When Oumuamua appeared in 2017, it immediately sparked intense scientific debate with its strange non-gravitational acceleration, highly unusual elongated shape, and complete lack of visible cometary activity. These puzzling characteristics led some prominent researchers to propose increasingly exotic explanations, including the genuinely controversial possibility of artificial origin. Harvard astronomer Avi Loeb famously argued that Oumuamua could represent alien technology, specifically a light sail constructed by an extraterrestrial civilization. The object's acceleration pattern, unusual reflectivity, and elongated dimensions seemed inconsistent with natural cometary behavior, creating a scientific mystery that remains unresolved. 3I Atlas presents an entirely different and refreshingly straightforward story. Early observations revealed unmistakable signs of normal cometary activity that matched theoretical predictions perfectly. Multiple telescopes detected a faint but clearly visible coma and a tail stretching at least 25,000 kilometers through space, definitively confirming its status as a genuine comet. The object displays all the expected properties of a comet that formed naturally in the cold outer regions of another planetary system. Its overall composition and behavior appear remarkably similar to comets found in our own Kuiper belt, strongly suggesting that universal physical processes govern comet formation across different stellar environments. Unlike Oumuamua's deeply puzzling behavior, 3I Atlas follows completely predictable orbital mechanics, without any anomalous accelerations or trajectory changes that might suggest exotic physics or artificial propulsion. The comet's path through our solar system conforms exactly to gravitational calculations based on its observed mass and velocity. Spectroscopic analysis reveals normal cometary compositions, including water vapor, carbon monoxide, and organic compounds that match expectations for objects formed in planetary system outskirts. The reddish coloration of its coma indicates dust content similar to the previous interstellar comet Borisov, supporting consistent formation processes. 3I Atlas represents exactly what scientists hope to find: interstellar objects that teach us about planetary formation through familiar, well-understood physics, rather than baffling mysteries that challenge fundamental assumptions about how the cosmos works. Mario Juric describes 3I Atlas as a potential tiebreaker that could help determine whether Oumuamua was genuinely anomalous or whether the universe contains more exotic objects than previously imagined. The normal behavior of 3I Atlas supports the hypothesis that most interstellar visitors will prove to be conventional comets and asteroids ejected from other planetary systems during chaotic formation phases. October 3rd, 2025 will mark an unprecedented moment in space exploration when 3I Atlas makes its closest approach to Mars at a distance of just 29 million kilometers, giving orbital spacecraft the best views ever obtained of an interstellar visitor. Mars orbiters, including the Mars Reconnaissance Orbiter, Mars Express, MAVEN, and the HOPE probe, will have extraordinary opportunities to study this cosmic wanderer with instruments originally designed for planetary science, but perfectly suited for detailed cometary observations. From Mars's perspective, 3I Atlas may reach apparent magnitude 11 during closest approach, making it easily detectable by high-resolution cameras and scientific instruments already positioned in the Martian system. This brightness level places the comet well within detection capabilities of existing spacecraft. The Mars Reconnaissance Orbiter's high-rise camera, capable of resolving features smaller than 1 meter across on the Martian surface, could potentially capture unprecedented detail of the comet's nucleus structure and surface features. These observations would provide the highest resolution images ever obtained of an interstellar object. Spectroscopic instruments aboard Mars orbiters can analyze the chemical composition of 3I Atlas's coma and tail with exceptional precision. The MAVEN spacecraft's ultraviolet spectrometer could detect trace gases and atmospheric escape processes, while Mars Express's infrared spectrometer can identify complex molecular species. The timing of the encounter allows for extended observation campaigns as the comet approaches, reaches closest distance, and recedes from Mars. This temporal coverage enables scientists to track changes in cometary activity, coma development, and tail structure as solar heating intensifies during the final approach to perihelion. Mars-based observations will be complemented by simultaneous measurements from Earth-based telescopes, creating a comprehensive three-dimensional view of the comet's structure and activity patterns. The different viewing geometries provide stereoscopic information impossible to obtain from any single vantage point. The European Space Agency's Mars Express mission is planning coordinated observations with ground-based telescopes to maximize scientific return from this rare opportunity. These measurements will create the most detailed characterization ever achieved of an interstellar visitor's physical properties. The close approach also presents unique opportunities for studying gravitational interactions between the comet and Mars. While 3I Atlas is too small to significantly affect Martian motion, precise tracking could reveal subtle perturbations that constrain the comet's mass and internal structure. Future Mars missions may specifically target interstellar objects for close-up study, potentially including sample return missions that could bring pieces of alien worlds back to Earth for laboratory analysis. The discovery of 3I Atlas coincides perfectly with a revolutionary transformation in astronomical surveying capabilities that will turn rare interstellar visitors into routine scientific observations, fundamentally changing how we study cosmic wanderers. The Vera C. Rubin Observatory in Chile represents the most advanced sky survey system ever constructed, designed to scan the entire southern sky repeatedly every few nights for 10 years. Its massive 3.2 gigapixel camera captures images covering 3.5 degrees of sky in just 15 seconds. During its first week of operation, the Rubin Observatory discovered over 200 previously unknown asteroids, demonstrating extraordinary capability for finding moving objects. This detection rate far exceeds what all other ground and space-based observatories combined typically discover in an entire year. Mario Juric explains that as the observatory's survey progresses, it should uncover many more visitors from beyond our solar system, allowing astronomers to study them as a population rather than scattered, isolated discoveries. Current estimates suggest the facility will discover between 1 and 10 interstellar objects annually once it reaches full operational capacity. The automated systems can identify potentially interesting objects within minutes of capturing an image, comparing new observations with previous data to flag anything that moves, brightens, or exhibits unusual behavior. This rapid processing capability means future interstellar visitors will be detected and tracked from their very first appearance. The observatory's wide field of view and rapid scanning capability will solve detection bias problems that nearly caused 3I Atlas to go unnoticed. Even objects passing through crowded star fields near the galactic center will be detectable using sophisticated image processing algorithms designed to identify subtle motion patterns. Future space-based survey systems will further revolutionize interstellar object detection by eliminating atmospheric limitations and providing continuous sky coverage. The European Space Agency's planned missions could detect much fainter objects across wider areas of sky, potentially revealing the true abundance of cosmic wanderers. Advanced artificial intelligence systems will process the unprecedented data volumes, identifying scientifically interesting targets among millions of routine observations. Machine learning algorithms trained on 3I Atlas and future discoveries will improve detection efficiency and reduce false positives. The statistical sample of interstellar objects will grow large enough to answer fundamental questions about planetary system evolution throughout the galaxy. Comprehensive catalogs will reveal size distributions, composition variations, and origin patterns that illuminate how different types of stars produce and eject planetary building blocks. Long-period surveys spanning decades will track how interstellar object populations change over time, potentially revealing periodic variations linked to galactic dynamics or stellar evolution cycles. This technological revolution ensures that 3I Atlas represents the beginning, not the culmination, of interstellar object science. After 3I Atlas completes its spectacular passage around the Sun and begins its journey back into interstellar space, it will carry whatever secrets it holds into the cosmic void, never to return to our solar system or any other star system for millions of years. The comet's hyperbolic trajectory ensures that it will exit our solar system at nearly the same velocity it entered, approximately 68 kilometers per second relative to the Sun. After gaining additional speed from solar gravitational acceleration during perihelion passage, 3I Atlas will race outward past the orbits of Jupiter, Saturn, Uranus, and Neptune. By March 16, 2026, the comet will pass within 54 million kilometers of Jupiter, receiving a final gravitational boost that will increase its exit velocity even further. This encounter represents the last significant gravitational interaction 3I Atlas will experience before leaving our cosmic neighborhood forever. Once beyond the orbit of Neptune, the comet will begin its return journey to the frigid depths of interstellar space, where temperatures approach absolute zero and deadly cosmic radiation will gradually alter its surface composition over millions of years. The active coma and tail will fade as solar heating diminishes, leaving only a dark, inactive nucleus drifting through the void. The journey back to interstellar conditions will take decades as 3I Atlas slowly recedes from solar influence. At distances beyond 1,000 astronomical units, the Sun will appear as merely another star in the cosmic background, providing negligible heating or gravitational effects. During its extended voyage through the galaxy, 3I Atlas will encounter the gravitational fields of other stars, potentially altering its trajectory and velocity over millions of years. These stellar encounters could eventually redirect the comet toward entirely different regions of the Milky Way. The comet might eventually approach another star system where it could be captured into a new orbit or continue its wandering journey. If captured, 3I Atlas could become a permanent member of an alien planetary system, carrying chemical signatures from our solar system to worlds beyond imagination. Alternatively, the comet could drift through interstellar space for billions of years without encountering another star, slowly degrading under cosmic radiation until only a dark remnant remains. The organic compounds and water ice that define its current composition will gradually transform into simpler chemical species. The scientific data collected during 3I Atlas's brief visit will continue providing insights long after the comet disappears. Detailed analysis of spectroscopic measurements, brightness variations, and compositional data will occupy researchers for years, revealing new understanding of planetary formation processes throughout the galaxy. Future interstellar visitors will be compared against 3I Atlas's properties, building comprehensive databases that illuminate the diversity of planetary systems and the mechanisms that eject objects into galactic wandering. The European Space Agency's Comet Interceptor mission, scheduled to launch as early as 2029, represents humanity's best hope for achieving an unprecedented close encounter with an interstellar visitor, potentially including 3I Atlas if trajectory calculations prove favorable. Colin Snodgrass, an astronomer at the University of Edinburgh working on the ESA mission, explains that there is a small chance that Comet Interceptor might be able to visit an interstellar object if one is found on the right trajectory, and the new Vera C. Rubin Observatory should give us an increased rate of discovery of these objects. The Comet Interceptor spacecraft will wait in space at the L2 Lagrange point, positioned to intercept any suitable target that approaches within reasonable range. This Sentinel strategy allows for rapid deployment toward objects discovered after launch, including potential interstellar visitors that cannot be predicted in advance. The mission consists of 3 separate spacecraft that will approach their target from different angles, providing comprehensive 3-dimensional observations impossible to achieve from any single viewpoint. This multi-spacecraft configuration could revolutionize our understanding of interstellar object structure and composition. Advanced instruments aboard the interceptor spacecraft include high-resolution cameras, mass spectrometers, and dust analyzers, capable of determining precise chemical compositions and physical properties. These measurements would provide unprecedented detail about materials from another star system. A successful interstellar object encounter would represent one of the most significant achievements in space exploration history, comparable to the first moon landing or Mars rover missions. The scientific return from direct analysis of alien materials could answer fundamental questions about planetary formation and the potential for life throughout the galaxy. The mission timeline creates urgency for maximizing observations of 3I Atlas and future interstellar discoveries. Each new visitor provides additional targets for potential spacecraft encounters while improving our understanding of interstellar object populations and trajectories. Sample return missions represent the ultimate goal for interstellar object science. Bringing pieces of alien worlds back to Earth for laboratory analysis would provide insights impossible to achieve through remote observations, potentially revealing complex organic compounds or even biosignatures. Advanced propulsion technologies currently under development could enable rapid response missions to newly discovered interstellar objects. Ion drives, solar sails, and nuclear propulsion systems might allow spacecraft to achieve the high velocities necessary for intercept trajectories. International cooperation will be essential for successful interstellar object missions. The global astronomical community's coordinated response to 3I Atlas demonstrates the collaborative framework needed for future spacecraft encounters with cosmic wanderers. 3I Atlas represents far more than an astronomical curiosity. It serves as a cosmic messenger carrying profound implications for humanity's future in space and our understanding of life's potential throughout the galaxy. This interstellar visitor connects us directly to the broader universe, reminding us that our solar system exists within a dynamic galactic environment where material and information flow freely between star systems. The chemical signatures preserved in 3I Atlas's ancient nucleus provide direct samples of conditions that existed in another planetary system billions of years ago. Each spectroscopic measurement and compositional analysis adds crucial data to our growing understanding of planetary formation processes throughout the galaxy. The accumulation of observations from 3I Atlas and future interstellar visitors will eventually allow comprehensive statistical analysis of conditions in numerous stellar environments. The diversity of interstellar objects likely reflects the tremendous variety of planetary systems throughout the Milky Way. Some visitors may come from systems dominated by gas giants, others from regions rich in rocky worlds, still others from environments unlike anything in our solar system. Each messenger carries unique information about its place of origin. The detection of complex organic molecules in interstellar objects would represent one of the most profound discoveries in human history, potentially providing evidence that the chemical precursors for life are widespread throughout cosmic environments. Even simple organic compounds would demonstrate that life's building blocks are common in the galaxy. Advanced missions to intercept and study interstellar objects could return physical samples to Earth for detailed laboratory analysis, providing unprecedented insights into alien materials and chemistry. Future spacecraft might even be designed to follow interstellar visitors back into deep space, extending our exploration capabilities beyond the solar system. Educational initiatives inspired by 3I Atlas are cultivating new generations of scientists and engineers who will develop revolutionary techniques for studying cosmic messengers. Student involvement in real research projects provides authentic experiences that inspire continued engagement with space science and exploration. International cooperation in interstellar object research establishes frameworks for sharing data and coordinating observations that benefit future discoveries. These collaborative networks ensure that humanity's response to cosmic visitors maximizes scientific return while engaging diverse global perspectives. The successful study of 3I Atlas proves that our technological capabilities have reached the threshold necessary for routine interstellar object science. Advanced survey systems, sophisticated instruments, and coordinated global observations now provide the tools needed to extract maximum value from these rare opportunities. As 3I Atlas completes its journey through our solar system and returns to the cosmic deep, it leaves behind a transformed scientific community equipped with new knowledge, enhanced capabilities, and elevated expectations for future discoveries. The age of interstellar archaeology has begun, offering unprecedented opportunities to study the galaxy's hidden history through direct examination of materials from distant worlds. The story of 3I Atlas will be remembered as the moment humanity truly began exploring the galaxy without leaving our solar system. This cosmic bullet, racing through space at 68 kilometers per second with the most extreme trajectory ever recorded, has shattered our understanding of what lurks in the darkness between stars. From its near miss with detection while hiding against the galactic center's billion-star backdrop, to the shocking revelation that amateur astronomers had been tracking it for weeks before professionals recognized its alien nature, 3I Atlas exposed critical weaknesses in our cosmic surveillance systems while demonstrating the power of citizen science. The mathematics are undeniable. An orbital eccentricity of 6.2, speeds that dwarf previous interstellar visitors, and size estimates that could make this the largest cosmic wanderer ever detected. These numbers encode a story of violence and survival that stretches across millions of years and countless light-years of space. But perhaps most importantly, 3I Atlas has proven that our galaxy teems with interstellar objects carrying chemical signatures from alien worlds. University of Hawaii's John Tonry's admission that quite a few come through our inner solar system each year means we're surrounded by cosmic messengers waiting to reveal their secrets. The race against time is real. Mars orbiters will capture unprecedented images in October. The James Webb Telescope will unlock infrared secrets invisible to human eyes. Ground-based observatories worldwide are coordinating the most intensive study of an interstellar object in history. And then, after its brief moment in our cosmic spotlight, 3I Atlas will vanish forever into the void, carrying whatever mysteries remain back to the galactic darkness where it will drift for millions of years before potentially encountering another star system. The future promises even more remarkable discoveries. The Vera C. Rubin Observatory will transform rare visitors into routine science. Interceptor missions may achieve humanity's first close encounter with materials from another star system. Each new cosmic wanderer adds pieces to the greatest puzzle in astronomy, understanding how common worlds like Earth might be throughout the galaxy. 3I Atlas has opened our eyes to the reality that we live in a universe where alien worlds regularly visit our cosmic doorstep. The chase may be ending for this particular visitor, but the greater journey of cosmic archaeology has only just begun.